When learning about the laws of physics, you find that there are a large number of complicated and detailed laws. The laws of gravitation, of electricity and magnetism, nuclear interactions, and so on and so on. But across the variety of these detailed laws, there sweep great general principles, which all the laws seem to follow. Now, these principles are, for instance, the principles of conservation, certain qualities of symmetry, the general form of quantum mechanical principles, and unhappily or happily, as we spoke about last time, the fact that all the laws are mathematical. And tonight I want to talk about the conservation principle. Now, a principle of the physicist uses all ordinary words in a peculiar manner, which is unfortunate. For example, conservation law means this, the way he uses the word, is that there is a number which you can calculate at one moment, and as nature undergoes its multitude of changes, this number doesn't change. That is, if you calculate again this quantity, it'll be the same as it was before. An example is the conservation of energy. There's a quantity that you can calculate according to a certain rule, and it comes out the same answer after no matter what happened. Now you can see that such a thing is possibly useful. It's analogous to this. Suppose that the physics or the nature is made analogous to a great chess game that we're watching with millions of pieces on it, and we're trying to discover the laws or the rules by which the pieces move. And the great gods who play these chess play it very rapidly. It's hard to watch, and it's difficult to see, and we're catching on to some of the rules. But there are some rules which we could work out which do not require that we watch every move. For instance, if there's one bishop only on the board, since the bishop moves diagonally, it never changes its color. So if there's a red bishop on the board and we look away for a moment while the gods play for a few minutes, look again, we can expect that there's a red bishop on the board. Maybe in a different place, but the same the same color, square. And this is in the nature of a conservation law. We don't need to watch the insides, but we at least know something about the game anyway. It's true that in chess, this particular law is not necessarily perfectly valid. If we watch long enough, it could happen that the bishop is captured while we weren't looking, a pawn went down to queen, and the god decided that it was better to put a bishop instead of a queen in the place of that pawn, and it was on a black square. And so, unfortunately, it may well turn out that some of the laws which we see today may not be exactly perfect, but I'll tell you how it looks now. I said that we use words in a technical fashion, and another word in this title is the Great Conservation Principles. This is not a technical word. It was merely put in to make the title sound more dramatic. Just as well call them the conservation law. If you wish, there are a few conservation laws that don't work, that are only approximately right, that are kind of useful, and we might call those the little conservation laws. I'll mention one or two of those. But the other ones that I'm going to mention are, as far as we can tell today, absolutely accurate. The easiest one to understand is the one I'll start with, and that's the conservation of electric charge. There's a number, the total electric charge on a thing, which, no matter what happens, doesn't change. Of course, the total electric charge in the world, rather, is what doesn't change. The charge may go from one place to another, but if you lose it here, you'll find it over there. So the conservation is of a total of the electric charge. This was discovered experimentally, or demonstrated experimentally, by, I am embarrassed to say, I don't remember whether it was, I think it's Faraday, but it might have been Franklin. Anyway, it's somebody whose name begins with F. And I know at least this much, that it isn't Feynman anyway, but it's... At any rate, the experiment consisted of getting inside of a great globe of metal, on the outside of which was a very delicate galvanometers to look for charge on the globe, because small amounts of charge would make a big effect. And then inside the globe, this experimenter, whose name began with F, built all kinds of weird electrical equipment of every kind. He made charges by rubbing glass rods with cat's fur, and he made big electrostatic machines run inside and so on, so that the inside of this thing looked like those horror movies laboratories. And during all these experiments, no charge developed on the surface. There was no net charge made. When a glass rod was charged up with the cat's fur, although the rod may have been, I forget, say, positive, then the cat's fur would be the same amount of charge negative. Because the total charge was never anything. If there were any charge developed on the inside, it would have appeared as an effect in the galvanometer on the outside. So the total charge is conserved. Now, this one is an easy one to understand because a very simple model that's not mathematical at all will explain it. Suppose that the world is only made of two kinds of particles, electrons and protons. There was a time when it looked like it was going to be as easy as that. And that the electrons carry a negative charge and the protons a positive charge, so we can separate them. We can take a piece of matter and put more electrons on or less electrons. But suppose that electrons are permanent. They do not disintegrate. They never disappear. That's all. Now, that's not even mathematical. That's a simple proposition. And now you see that the total number of electrons take away, or the protons rather, take away the number of electrons won't change. As a matter of fact, the total number of protons won't change, and the total number of electrons won't change in this particular model. But we're concentrating now on the charge. And the difference, the contribution of the positive, of the protons is positive and the electrons is negative. And if these objects are never created or destroyed alone, then the total charge will be conserved. I want to list later on the number of properties of conserved quantities, and I start with the one about charge that we're talking about, and we mark down here that it is conserved. And that's the beginning. This goes yes. So that's the first. The chart will expand as we go along. This theoretical interpretation is very simple, but it was later discovered that electrons and protons are not permanent. For example, a particle called a neutron can disintegrate into a proton and an electron, plus something else which we'll come to. But the neutron, it turns out, is electrically neutral. So although protons are not permanent, nor are electrons permanent in the sense that they can be created from a neutron, the charge still checks out, because starting before we had zero charge, and afterwards we have +1 and -1, so when added together, you get zero charge. So that the rule is, now another example of a similar trouble, not trouble, but fact, is this, that there exists another particle which is positively charged besides a proton called a positron, which is a kind of an image of an electron. It's just like the electron in most respects, except it has the opposite sign of charge, and more important, it's called an antiparticle because when it meets with an electron, the two of them can disintegrate, they can annihilate each other, and nothing but light come out. So electrons are not permanent, even by themselves. An electron plus a positron will just make light. Or actually, the light is invisible as gamma rays, but it's the same thing for a physicist. Just the wavelength is different. So a particle and the antiparticle can annihilate. The light has no electrical charge, but we remove one positive and one negative charge, so we haven't changed the total charge. Therefore, the theory of this conservation of charge is a little slightly more complicated, but still very unmathematical. It's simply this. How many positrons do you have? How many protons? Take away the number of electrons. And there are other particles, it turns out, in the world that you have to check. For instance, there are antiprotons. They contribute negatively. There are positive pi mesons. They contribute positively. Each particle in nature has, fundamental particles have charges, and all we have to do is add the total number, and whatever happens in any reaction, the total amount of charges on one side has to balance on the other side. That's one aspect of the conservation of charge. Now comes an interesting question. Is it sufficient to say only that charge is conserved, or do we have to say more? If charge were conserved because it was a real particle which moved around, it would have a very special property. The total amount of charge in a box might stay the same in two ways. It may be that the charge moves from one place to the other in the box and just stays in the box. But another possibility is this. Charge here disappears. And simultaneously over here, charge arrives. In such a manner, instantaneously related, so that the total charge is never changing. This possibility for the conservation is a different kind than the other one, in which if anything happens that the charge goes away here, something has got to go through the in between. Something goes past you. If you stood there and watched, something would go by. The second form of charge conservation is called local charge conservation, and is far more detailed than the simple remark that the total charge doesn't change. So you see, we've been proving our law, if in fact it's true, that charge is locally conserved. It is true. That it must be true, of course, nothing can be proved without some other things, but as I desire to show you from time to time as much as possible some of the possibilities of reasoning interconnecting one idea with another, I would like to show you an argument which is fundamentally due to Einstein, which indicates that if anything is conserved, and in this case I apply it to charge, it must be conserved locally, provided one thing, provided that if two fellows are passing each other in a spaceship, the argument about which guy is doing the moving and which one is standing still cannot be resolved by any experiment. That's called the principle of relativity, that the motion is relative and that we can look at any phenomenon from either point of view, either from the point of view that the one is moving and that this one is standing still and this one is moving, or the other way around. Now, suppose I take this point of view that this one is the one that's moving past him. Don't forget, that's just temporary. You can also look at it the other way, and you must get the same phenomena of nature. Now, suppose that this man who's standing still wants to argue whether or not he sees a charge over here disappear and a charge over here appear at the same time. In order to make sure that it's the same time, he can't sit in the front of the ship because he'll see one before he sees the other on account of light. So let's suppose that he's very careful. He sits dead center in the middle of the ship, right here, and looks. He's right in the middle, halfway in between. Incidentally, I'm going to have another man doing the same kind of observation in the other ship. And now, a lightning bolt strikes and charge at this point A is created at a certain instant. And at the same instant, back over here, at this place B, on the other side, in the back of at the other end of the spaceship, funny-looking spaceship, the charge is annihilated, disappears at the same time, which is perfectly consistent with our idea that charge is conserved, because if we lose one electron, we get one electron here and lose one here, but nothing went in between. Now, see. He says at the same time, he watches, he sees it's exactly the same time, because the light which comes from the bolt which created the A reaches him at the same time as the light which comes from the flash of disappearance. We suppose that when it disappears, there's a flash, and when it's created, there's a flash, so we can see what happened. And then we see the two flashes at the same time, and since he knows he's in the middle of the ship, he says, yes, when one disappeared, the other was created. But what happens to our friend in the other ship? He says, no, you're wrong, my friend. I saw A was created before B. Because the light is coming out of A, but the man is moving toward it because he's moving. And the light hits him from the front before the light can reach him from the back because he's moving away from the light. So by the time the light gets here, he's got moved over. So he says, no, A, you see, was created first, and then B disappeared. So for a short time, after I saw A was created,